Okay, this is a nice little linear algebra question. Actually comes from the entrance exam for engineering students, Flemish universities, and you can see that only 30% of the applicants have answered this correctly. So if you want to try it yourself, you can read the question, pause the video and have a go at it. So the question is, consider the system in unknowns xyz, element r, and parameter a, element r. Does that x plus y plus a times z is a plus 1, x plus a y plus z is a plus 2, and ax plus y plus z is a plus 3. Which of the following statements is the false one? And then it's about unique solutions and different values for a. So we can see if we take the matrix and then the determinant of this system. So the matrix will be 1, 1a, 1a, 1, and a, 1, 1. So the determinant is, so you cover this one, 1 times a times 1 minus 1, 1, 1 times 1, and then minus 1 times 1 times 1 minus a times 1, and then a plus a times 1 times 1 minus a times a, which gives you 1 times a minus 1 minus a 1 times a minus a plus a times 1 minus a squared, or a minus 1 plus a minus a to the third, or minus a to the third plus 3a minus 2. So if this is 0, that means we either have 0 or infinite solutions. So does this have zeros? Well, we can test, and usually we do that by guessing a bit. The last constant term is minus 2, so you can write that as plus or minus 1 times minus or plus 2, and then try one of these and to see if this gives you a 0, and we're lucky because 1 immediately gives us a 0. So 1 is a 0 of this. Then you can use Horner to get the other coordinates. So minus 1, we have no a squared, so that's 0. Then we get 3, and then minus 2. We drop to minus 1. We write the 1 here because we know it's divisible by 1. So 1 minus 1 is minus 1. Sum this gives minus 1. 1 minus 1 is minus 1. 3 plus minus 1 is 2. 1 times 2 is 2. Minus 2 plus 2 is 0. So it is indeed divisible. So we get a minus 1 times minus a squared minus a plus 2 is 0. We do the same trick, and you can see that this is again divisible by 1. We're in luck. And we can do Horner again. So we have minus 1, and 2, and then divisible by 1. Drop the 1 and the minus 1, so 1 minus 1 minus 1. Plus minus 1 is minus 2. 1 minus 2 is minus 2. 2 and minus 2 is 0. So you can write this as a minus 1 times a minus 2. The other 0 is obviously a is minus 2. So you actually have a double root. A is 1, and then the other root is a minus 2. So if you fill in a is 1, then you get x plus y plus z is 1 plus 1, x plus a plus z is 1 plus 2, and x plus I plus z is 1 plus 3. Yeah, well, it can't be 2 or 3 or 4 at the same time, so this has no solution. If you fill in a is minus 2, then you get x plus y minus 2z is minus 2 plus 1 is minus 1, and x minus 2y plus z is minus 2 plus 2 is 0, and minus 2x plus y plus z is minus 2 plus 3 is 1. And if you sum all those three up, then you can see you get x plus x minus 2x, y plus y minus 2y, z plus z minus 2z, so 0 plus 0 plus 0 is 0, which means that these three are not independent. And if they're not independent, you have infinite many solutions. So that means answer B is false, and answer B was there exist at least two different values of A for which the system has no solutions. This is false because there's only one value of A being 1, for which that system has no solutions. The other value has infinitely many solutions. For all the other things, the system has a unique solution, and there is also a unique value of A minus 2, for which the system has infinitely many solutions. So only B here is the false one. So here you see this in Desmos, and if we change that to 1 and stop this, you can see these three planes, x plus y plus az is a plus 1, and the other two are perfectly parallel. So no points in common, so no solutions. If I go to a is minus 2, and yeah, now we have to, you can see here that the three planes, red, gray and green, intersect at a line, just one line. So a line as intersection has infinitely many points, so infinitely many solutions. Every other value of A, you can see that there's the three planes just intersect in one point, so it has one solution. It's fun to play with or let it run. But so this is the graphical interpretation of these this system, this linear algebra problem.